Hi there everybody, Augie Kennedy here, back with super awesome calculus. We're in chapter 2 now, which is Take It to the Limit, and today we're going to be covering section 2.2, and that is the limit of a function. So we're going to we introduced the idea of a limit through the tangent and velocity problems last time. This time we're going to look more in algebraic terms and graphical terms exactly what a limit is. But before we do that, let's go over the big problem from last time. The problem was, if a ball is thrown into the air with a velocity of 40 feet per second, its height in feet t seconds later is given by y equals 40t minus 16t squared. And I asked you to find the average velocity for the time period beginning when t equals 2 and lasting half a second, a tenth of a second, 5/100ths of a second, and 1/100ths of a second. And I also asked you to use that information to estimate the instantaneous velocity when t equals 2. Now, when you're approaching this, you want to remember what that function was last time for average velocity. And we learned that average velocity is change over change. And here we have change in time. And here we're going to have change in y. Let's put it that way. And the way that you do this, it's easier to put change in y so you understand exactly what you're plugging in here. So if y equals 40t minus 16t squared, the difference that you're going to put in the bottom is going to be the difference between 2 minus, or 2.0 or 2.5 minus 2 for the first one. Second one is going to be 2.5 minus, or 2.1 minus 2, etc., etc., etc. That's what your denominator is going to look like. Should be getting, eventually the denominator, you'll be getting a smaller and smaller decimal. Now, as far as the top, all you're going to do is you're going to plug in those t values into this function. So y equals plug in to, I mean obviously there are some that you can't plug in, but you plug in any value that can work here and yield a non-zero result. And so you're going to plug in t equals 2.5, you're going to plug in t equals 2, you're going to plug in all of the different t variables that you use in the denominator. And if you use these two functions, what you're going to get is something like this. For problem 1, you're going to get negative 32 feet per second. For number 2, you're going to get another negative number. Note these are negative because the t squared is larger. Negative 25.6 feet per second. For part 3, you're going to get negative 24.8 feet per second. And for part 4, you're also going to get a negative, and that was going to be negative 24.16 feet per second. Now let's look at the time intervals here. Half a second, tenth of a second, a 20th of a second, and a 100th of a second. Now if we look at that information right there, it should be pretty easy to see that these numbers are trending, that as this decimal gets smaller, as the time interval decreases, these numbers are trending from 32 to 25, make a make-believe graph, to 24.8 to 24.16, and you can see they're going to kind of slope, and it looks as if they're approaching 24, negative 24. And if you guessed that, you're right, because the answer to part B, a good estimate for the instantaneous velocity at t equals 2 is negative 24 feet per second. So if you got that, pat yourself on the back. Now, we're going to look at the idea of a limit more explicitly. Last time we talked about the idea of a limit by dragging two numbers, 2 points, either whether they be graphical points or velocity or time intervals, making the intervals shorter and shorter and shorter and shorter until they came very close to, but not quite at, a particular number. Now let's take a function. Let's take this function right here. F of x is x squared minus x plus 2. Okay? Now, what we want to do is let's say we want to find out what the limit is. Limit when x equals 2. Now the way that we talked about finding this is first we pick two numbers. Let's make a little table here. We'd pick two numbers. We'd pick x could be 1, x could be 3, x 1.5, x is 2.5, x is 1.9, x is 2.1. And we can just keep getting closer and closer. You just plug that value, that 1 squared is 1 minus 1 plus 2 equals 2. 3 squared is 9 minus 3 is 6 plus 2 is 8. And you can plug in 1.5 and you can do the same thing. You're going to get numbers that are trending closer and closer and closer to a certain point. Of course, what we can also do in this particular case is hopefully you're actually going to do the work and get through this. But if you don't, let's just try a direct substitution. Let's just put it right in. Let's try 2. 2 squared is 4 minus 2 is 2 plus 2 is 4. So the way that we say this is that the limit of this function as x gets closer and closer to 2 is 4. It's not saying, I mean, obviously if x is 2, the function does come out to be 4. The thing is that we're not really talking about what it is. Remember, a limit isn't really concerned with what something is. It's concerned with what something is very close to be. So, the way that we write this is like such. The limit, LIN, as x approaches 2 of the function x squared minus x plus 2 equals 4. Now when we figure out a limit, very often we're going to be dealing with concrete numbers. So you will be, when you're solving a limit, you're either going to be working with a number, an integer, or just a real number, or you're going to be dealing with something like infinity, which we'll talk about soon. So, now that we know the notation for a limit, let's go over the actual definition that the book gives. The definition they give is the limit of x, generally speaking, this is not the precise definition of a limit, more on that later. Limit as x approaches a, just like the last one, put a little arrow, of f of x equals L. And L is a number if that limit does in fact exist. Okay? Now, what we're going to go over is we're going to look at a couple limits here. We're going to analyze a couple functions, and we're going to see whether or not we can find a limit. We're going to use a fun trigonometric type function. This one is a pretty good example that you'll see pretty often in most calculus courses, and that is the limit. We're going to find the limit as x gets closer and closer to 0 of the function sine x over x. Okay? Now there are there are a lot of ways that you can do this. As it turns out, there's one very, very easy way to do this, which we will talk about when we talk about L'Hopital's rule. But for right now, the best way to do this is to just plug in values. So we can plug in 1, we can plug in plus and minus 1, we can plug in plus and minus a half, plus and minus a tenth, plus and minus 0.05. Go ahead, and you have full permission to use a calculator for this exercise. Go ahead, plug in x equals 1, plug in x equals negative 1. Write down what you get. You should get 0.84 something. X equals 0.5, you should get 0.96 something. 0.1, you're going to get 0.99, and then 0.05, you're going to get the same thing. Actually, you're going to get 0.999, you're going to get a whole bunch, you're going to get a number very, very, very close to 1. And in fact, that is the limit. So we say that the limit as x approaches 0 of sine x over x equals 1. And if we look at the graph of that function, we'll see that that is in fact what happens. You can see that the function isn't defined, it's open. It's not defined at 0, but we can see that on this side it is getting close to 1, and on the right side it's also getting close to 1. And this is going to lead us into our discussion of one-sided limits. As soon as we look at one other example, just remember, you see how it's not defined there. If you 0, limit of x equals 0, if we plug 0 in, we get sine of 0, which is 0 over x equals 0 is 0. We get 0 over 0. It's indeterminate form. We can't use that, so we use this method, the method of exhaustion. So now, what we're going to do is we're going to look at another example. Let's look at this limit. The limit as x approaches 0 of sine pi over x. Okay? Now, we can guess from what we did last time, when we had sine x over x, that the limit might be 0. Let's try plugging it in. Right away, we get the limit of sine of pi over 0, which is indeterminate. We can't do anything with it, so direct substitution fails. So what we're going to do is we're going to plug in various things. Let's plug in, if sine pi over x is f of x, let's plug in f equals 1. We get sine of pi. We know that's 0. If we plug in f of a third, we get sine of 3 pi, which is 0. F of a tenth, we get sine of 10 pi equals 0. And you can keep going, and you're going to keep getting 0. So we can guess from this that the limit is going to equal 0. But we'd be wrong. We'd be wrong because here's what's going to happen. If you remember last time, graphically, for sine x over x, while the function was not defined, it had an open point at 0, from the left or from the right, the function was getting very close to 1. Here is what the function sine pi over x looks like. And what it's doing is it's going in waves, and then those waves are getting tighter and tighter and tighter and tighter together. And what that's called, that's an oscillating function, and it's not going to have a limit because it's basically just going to be going up and down in narrower intervals, but it's never going to stabilize towards something. So this limit, we don't have one. And when that's the case, we say that the limit does not exist, or DNE, does not exist. Limit of, as x approaches 0, sine pi over x. Now back to this idea of one-sided limits. Sometimes a limit will approach from one direction but not from the other. So let's look at a function. I'm going to make one up right here. Here's a graph. 1, 2, 3, -1, -2. Let's go out to -3, 1, 2, 3, -1, -2, -3. Okay? Here's our function. Open. Open. Okay. So what we see here, we see two functions graphically. If I asked you what is the limit of f of x at x equals 0, you might have a tough time answering this because you'd be looking at the right-hand side, and looking at the right-hand side you'd be like, well, it looks like it's going down to 2. But if you look from the left-hand side, you'd be like, well, you know, but right here it looks like it's going to 1. Well, you're right in both cases. This is the notion of one-sided limits. And we write like this. LIM, as x approaches 0, from the, with a negative sign, from the left is 1. That's what the limit's approaching. But the limit as x approaches 0 from the right, coming down that line, is 2. These two limits disagree. So what is the limit? Well, you may have guessed that if the right-hand limit and the left-hand limit don't agree, then the limit does not exist. So therefore, this limit does not exist. However, I might choose to do something differently. I might choose the function to not be defined there and then continue like this. Two different shapes of function. The function takes on two different shapes. Here it looks kind of cubic of some sort, and then here it looks like a line. It looks linear. Well, here the limit from the left, limit as x approaches 0 from the left equals 1. And on the right-hand side, the limit as x approaches 0 from the right also equals 1. So now, the limit of this function at x equals 0 does exist, and it's 1. Which brings us to the theorem. Like I said, if both sides have limits that agree, the limit exists. Okay. Now, that takes care of that. We're going to look at infinite limits and vertical asymptotes. I know I'm really running out of time here, but it's important to just talk about this. Let's look at f of x equals 1 over x squared. Check this out. Since it's not 1 over x, we're not going to have to deal with a certain property that we're trying to avoid here. So here's what 1 over x squared looks like. Alright, you can see there's an asymptote. That's the graphical representation. What if I asked you the limit of this function? What's the limit? Well, here's what we do. We're going to go limit as x approaches 0 of 1 over x squared, and we're going to look at it from both the left and from the right. Well, we can just look at this. First of all, if we plug in 0, we get 1 over 0, which you can't have. And whenever you're dividing by 0, there is a very, 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 very good chance that you're going to be having a vertical asymptote. Where the function is undefined, there's a pretty good chance. So for instance, 2x, or 2 over x minus 3, if that's our function, if I ask you what the limit is at 3, we notice that 3 minus 3 is 0. There's a good chance In fact, that there's going to be an asymptote there, a vertical asymptote. So let's look at this function from the right. Well, from the right, it looks like as we get closer to 0, we're going to some really, really huge number. And from the left, we're also going to some really huge number. And in fact, that's exactly what's happening. Both of these limits are converging on infinity. Limit as x approaches 0 of 1 over x squared equals infinity. Now, we use infinity here. Just remember that infinity is not really a number. It's an idea. This limit doesn't really exist. It's not approaching L because infinity isn't a number. But it doesn't exist in a special way. Not only does it not exist, it doesn't exist and it's going on forever. So that's what a limit at infinity is. You can have functions that go towards positive infinity and negative infinity. If we look at f equals 1 over x, we have exactly that problem. Look at this. Got 1 over x. Okay, if we look at it from the right, if we look at the limit as x approaches 0, 1 over x, from the right, we're going towards infinity. If we look at it from the left, we're going to negative infinity. So now not only does it not exist, it's going to both positive and negative infinity. Now, let's see. The last thing to mention that leads into the big problem of the day is that sometimes asymptotes can be a little bit interesting. We know that the tangent function has vertical asymptotes, and you can prove this by taking tan x equals sine x cosine x. And you can realize that those asymptotes are going to occur when cosine x equals 0. And you can understand that it's going to intercept here when sine equals 0. So that's the way that, that's why tangent's graph looks like it does. Take something like the natural logarithm that has a natural graph, y equals ln x, that has a natural asymptote right here at the y-axis. Because remember, the smaller the number, if we're dealing with a decimal here, we're just going to go to a very, very large negative number. We're going to be going towards negative infinity. As we go positive, we're going to be dealing with a horizontal asymptote, but not really. It's going to be going to infinity as well. Don't worry about that part. Forget about that. Just focus on negative infinity for the natural logarithm graph. Which takes us into the big problem. I'd like you to determine the infinite limit of the function natural log of x squared minus 9 as x approaches 3 from the right. Please figure that out, and I'll see you next time. Thank you very much.